Okay, what's up, everybody? Welcome back. All right, so after talking a little bit about eigenvalues and eigenvectors, we're going to take a detour into something that at first seems a little bit unrelated, but will wrap back around into being extremely relevant. That is, we're going to talk about upper triangular matrices. What? We're talking about eigenvalues and eigenvectors abstractly, just for abstract linear maps between finite dimensional vector spaces, in particular, from a vector space to itself, that is, for operators. Where are these matrices coming from? Why do we need to care about them again? Well, it turns out that the ways you can make a matrix for an operator tell you a lot of things about the operator. So, just quick recap in case you don't recall. If we have a linear map from a vector space V to a vector space W, we can take a matrix for that linear map with respect to a basis for V and W. If we have an operator on a vector space, then since it's sending V to V, we can just do this with respect to one basis. That is, we can use the same basis for the domain and the codomain. So the matrix of an operator T on a vector space V with respect to the basis V1 through Vn of V, that is, we're assuming that V here is finite dimensional and has dimension n, since that's the length of one of its bases. Well, what we're saying is that we get a matrix MT whose entries are defined so that the image of the kth basis vector under T can be written as a linear combination of V1 through Vn, the elements of the basis, with coefficients coming from the kth column. So, if the basis isn't clear from the context, we'll explicitly put it in the notation for M. We won't have to write two separate ones, but just to recall, if T is an LVW and W1 through WM is a basis of W, V1 through Vn is a basis of V, then MT is the matrix such that T of Vk is equal to MT. Now I'm going to write it in exactly the same way. It'll be 1k W1 plus ... all the way down through MT MK WM. So what I'm trying to write here and trying to clarify is that this idea here these are the same idea, but with W equal to V and the same basis for both. Okay, so this is just a subcase of this previous notion we had. Let me zoom out a little bit so I can kind of keep everything in frame. So we have a matrix of a linear map. We've had that idea before. That's this right here, this definition. Now, in the particular case that our linear map is an operator, then we can do a matrix with respect to the same basis on the domain and the codomain, and that gives us the definition we have right here. So this is just like a simpler case. Don't think of it as something new. All right, the entries in the kth column tell you how to write the image of the kth basis vector under T as a linear combination of the basis V1 through Vn, which is the exact same as what's going on here with W1 through Wm. Just here, since W is equal to V, we can take W1 through Wm to be V1 through Vn, and M is in fact equal to N in that case. All right, cool. So here, quick example just to jog your memory. All right. So let's take, let's let T be a linear map on, say, R3. let's have it be defined by t of x, y, z is equal to, let's do 2x plus y, 5y plus 3z, and 8z. Then, with respect to WRT, the basis 1, 0, 0, 0, 1, 0, and 0, 0, 1. Put now my little boxes around that of F3. The matrix of T is just, okay, let's think about it. So if I punch the first basis vector through, I would get out, well, I'm putting in 1 for x and 0 in for y and 0 in for z. I would get 2, 0, 0, right? So that is, as a linear combination of these guys, it's 2 times the first basis vector plus 0 times the second plus 0 times the third. Now, if I put 1 in for y and 0 in for x and z, that is if I plug the second basis vector in, then I will get 1, 5, 0. Okay, so that's 1 of the first one, 5 of the second one in this basis, and 0 of the third. Now, finally, if I put z in equal to 1 and all the other ones equal to 0, I'll get 0, 3, 8. So that is 0 of the first basis vector, 3 of the second basis vector, and 8 of the third. There we go. 2, 1, 5, 3, and 8. Oh, look, if you kind of just look at what this t looks like, it just is the coefficients next to the x's and the y's going across in each row. So there's a 2 in the x one, a 1 next to y, there's a 5 next to y. Okay, there we go, right there, and a 3 next to z. Oh, there you go, that's the second row. And finally, there's an 8. All right, cool. Not too bad. So here's the gist. We're going to get a lot of information about what an operator does and is, and in particular, here's the spoiler, about its eigenvalues from how we can write a matrix for that operator. That is, if we can put it in a certain nice way, put it together in a certain nice way, make the matrix have a nice form, then we're going to get information about what its eigenvalues are. So here's the gist. We're going to need to care about the diagonal of a matrix. The diagonal of a square matrix, it's just all the entries on the line from the top left corner to the bottom right corner. Example. The diagonal of 2, 1, 0, 0, 5, 3, 0, 0, 8, that is the matrix for T that we just found, is circled here. So I'll circle it real quick in a nice color or something like that. I'll circle it, how about I circle it in like a nice teal here. It is particularly 2, 5, and 8. Okay, 2, 5, and 8. Kind of cool. All right, so diagonals. Let's keep going. All right, here's the idea, and this is what our main focus will be in this section. Upper triangularity. So a square matrix is said to be upper triangular if all the entries below the diagonal are 0. Example, the last matrix we just did. Okay, so here. The matrix, and I'll just grab that one really quick, just using a select so I don't have to rewrite it for everybody. Oh. What have I just done? I've made some kind of a mistake, sorry. Here. Zoom out. Did I just do some sort of mess? Oh. Okay, there we go. Now I've got it. Okay, whoa. Sometimes working with computers can be a little bit harder than I intend it to be. All right, oops, oop, there we go. So this matrix here, oop, and I've still somehow got something selected, and I don't want to have anything selected. Okay, there we go. This matrix is upper triangular. Sorry, guys. There we go. Technology. I should have just rewritten it. Here's one that's not. Let's do 1, 2, 3, 4, 5, 6, 7, 8, 9. How about? This one's not. Here, let's see why. So below the diagonal, these are all zeros. So in that upper triangle is the place where all of the entries could potentially, or where some of the entries could potentially be non-zero, but everything in the lower triangle is 0. Here, my lower triangle does not have all zeros. So here, all zeros, not all zeros. Okay, upper and lower triangular, not that bad of a concept. Just look at the diagonal. The stuff below it, is it all zeros? If it is, upper triangular. If it's not, oops, not upper triangular. So, what does upper triangularity tell us? Well, here's one thing it tells us. A bunch of different equivalent statements. So, I will write my proof box and we'll start to prove this guy. We'll take an operator on a finite dimensional vector space. We'll assume that v1 through vn is a basis for that vector space, and we'll call our operator t. The following statements are equivalent. The matrix of t with respect to that basis is upper triangular. Cool. All right. The equivalent statement is that the span of v1 through vk is invariant under t for each k between 1 and n. Oh. So the spans of sublists in that list, that is like truncated lists, are invariant under t for each truncation of the list forming your basis. And then finally, equivalent to this, as well as equivalent to the upper triangularity of t, is the statement that t of vk is in the span of v1 through vk for each k between 1 and n. Ooh, kind of cool. Okay. Among other things, let's look at this last one and think about it really quick. It says that t of v1 is in the span of v1, among other things, right? Okay, this tells us something cool. If t of v1 is in the span of v1, then v1 is an eigenvector for t. Upper triangularity tells you that t has eigenvalues. Whoa, or eigenvectors at least. All right, kind of cool. In fact, it has to have eigenvalues because you can't send a vector to something in its own span without just scaling it, right? So let's prove it. Okay, here's the proof for A implies B. Suppose MT is, I will say, UT, upper triangular, with respect to the basis V1 through Vn. Okay, now, then, T of Vj is equal to, well, I'll just write it down. It's MT 1 J V1 plus dot 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 all the way down through MT NJ Vn, which, notice, if the matrix is upper triangular, this means everything in the lower triangle is zeros. What are the entries there? Well, for example, here, this is the first column, second row, right? So this is a 2, 1, and this is a 3, 1, as in terms of the index corresponding to this entry right here. So whenever the first number is smaller than, or is bigger than the second, it goes away, so to speak. It's 0. So up to j, we could have some things that are non-zero, but after it, we can't. In fact, I'll just write that down right here in a nice, convenient way. mt1, or I missed a parenthesis right there, mt1 comma j, v1 plus dot 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 all the way up through mtj comma j, vj plus 0, vj plus 1 plus dot 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 all the way down through 0, vn. Potentially, this last part is a little bit of an abusive notation. If j is equal to n, then I shouldn't write this piece right there. And so maybe the technically slightly better way to write this, which I will do now that I've said it, is just to erase this, right? And just say it only goes up to the jth component. Since mt, I'll say I, j is equal to 0 for I greater than j. This is from upper triangularity. So tvj is in the span of v1 through vj, which, notice, is contained in the span of v1 all the way up through vk for k particularly bigger than or equal to j. So this is up through j. Sorry, this is a terrible j. For k greater than or equal to j. Okay, so just basically saying if you go up through the first j of them, well then if you put even more in there, it'd still be fine. Hence, we've shown now that upper triangularity implies that the span of v1 through vk is invariant under T. Oh, that is, T of vj is in the span of v1 through vk for k, or for j less than k, less than or equal to k. That is, every one of these elements, v1 through vk, that make up the basis for span of v1 through vk, gets mapped to something that lives in the span of v1 through vk. Hence, span of v1 through vk is invariant under T for k between 1 and n. Okay, cool. Now let's do B implies C. Suppose span v1 through vk is invariant under T for k between 1 and n. Okay, now we want to show that T of vk is in the span of v1 through vk. Then T of v is in the span of v1 through vk for any v in span of v1 through vk. Since vk is in the span of v1 through vk, we may conclude T vk is in the span of v1 through vk for k between 1 and n. Hey, we've just shown that B implies C. Okay, now let's show that C implies A. This finishes the proof, since we can go from any one to any other just by following this little circle around. So that C implies A, suppose tvk is in the span of v1 through vk for k between 1 and n. Then tvk is equal to, think about it real quick. I'll just write it this way, A1 V1 plus dot 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 all the way down through AK VK for some A1 through AK in F. But this means TVK is equal to A1 V1 plus dot 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 all the way down through AK VK plus, I will write it in the following way that is maybe not entirely correct, but is reasonable to say. I will say plus AK plus 1 VK plus 1 plus dot 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 all the way down through AN VN with AI equal to 0 for I greater than K. Now, why I said this is not entirely technically correct is that it could be the case that K is equal to N. Yeah? So maybe the better way to write this would be the following way that I think is slightly more instructive, but I think if I write it this way at first, it doesn't show what I'm really trying to say. That is, what I'm going to say is the following, A1 through, just that it's a sum of the basis V1 through Vn, a linear combination of those basis elements with these coefficients, and we're taking the coefficients to be 0 when they're larger. Okay. Since V1 through Vn is a basis, this representation, i.e. the coefficients, i.e. not EI, i.e. the coefficients A1 through AN are unique. I'll zoom out a tiny bit. But this gives TVK, by definition from the matrix, is MT1K V1 plus dot 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 MT NK Vn has the matrix of T, and I will write it this way, IK equal to 0 for I greater than K. That is, the matrix of T is upper triangular. Oh, yeah, that's the condition for upper triangularity. That is, what I'm saying is that if T of Vk is in the span of V1 through Vk, then I can write it as a linear combination of V1 through Vk. Since I can write T of Vk as a linear combination of V1 through Vn for sure, since V1 through Vn is a basis, this just means that the linear combination I get there is the one that takes the coefficients equal to 0 when they are next to a Vi with I greater than K. Oh, okay. This is a unique representation. Remember, with respect to a basis, every element can be written in one and only one way as a linear combination of those basis elements. Since the entries of the matrix are defined in terms of how to write TVK as a linear combination of V1 through Vn, and since I have found the one and only one way to do that, I can conclude that the entries in the matrix satisfy the condition that is equivalent to upper triangularity. That is, the matrix of T's ikth entry is equal to 0 whenever I is greater than K. Okay, cool. Sweet. Nice. Let's keep it going. Okay, it's time to blow your minds. Get ready. Upper triangularity maybe seems silly. Maybe it seemed like it wasn't doing too much for us. We did get one kind of nice piece with this last one where we said, hey, TVK is in the span of V1 through Vk for each K when T has a basis with respect to which its matrix is upper triangular. This did tell us that T of V1 is in the span of V1, so V1 is an eigenvector for T. Let me make it way better. All right, get ready. So, suppose that T is a operator on V, a finite dimensional vector space, and that V has a basis with respect to which T has an upper triangular matrix, and its diagonal entries are lambda 1 through lambda n. Then, get ready. T minus lambda 1i through T minus lambda ni, the product of all those guys, is the zero operator. What? This means that P of t is equal to 0, where P of z is the polynomial z minus lambda 1 through z minus lambda n. Oh, this must be a polynomial multiple of the minimal polynomial of t. So the minimal polynomial of t factors completely into linear terms. Whoa, nuts. That's crazy. Remember last time when we were talking about how sometimes you could end up with situations where the minimal polynomial didn't factor all the way? That is, things like x squared plus 1 over the reals, that doesn't factor any further, right? If you wanted to factor that, you'd have to use complex numbers. Okay, so what this is saying is that if T has an upper triangular matrix with respect to some basis, its minimal polynomial factors completely. That's actually kind of crazy. That's pretty neat. Moreover, all these values, or I shouldn't say all, yet, we will get to this. Moreover, some of these lambda i's are eigenvalues of T. In fact, lambda 1 through lambda n must contain all of T's eigenvalues. Why? Now, here's the gist. If this polynomial is such that P of t is equal to 0, then it's a multiple of the minimal polynomial of T. The zeros of the minimal polynomial are the eigenvalues of T. So this thing, if it's equal to 0, it doesn't necessarily mean that the minimal polynomial is equal to 0. But it means that all of the zeros of this guy, take the collection of all the zeros of this guy, that must contain all the zeros of the minimal polynomial. So the list lambda 1 through lambda n must at least contain all of the eigenvalues of T. We'll get a little bit further and we'll be able to say some more stuff. For example, are all of these actually just all the eigenvalues? Is there any extra information? We'll find out soon. But it at least contains all of the eigenvalues of T just from preliminary first inspection. So let's prove this cool fact. So by the way, just to note here, V has a basis, this part where we say T is an operator and V has a basis with respect to which T has an upper triangular matrix. This means that V has to be finite dimensional, since only finite dimensional vector spaces have a basis in the way that we've defined a basis. Okay, so proof. All right, let's do it. And by the way, let me take this and kind of put it off to the side. Okay, now for the proof of this, let's try it. We'll have to do a little trick. We're going to kind of just do a little procedure. So let's let V1 through Vn be a basis of T such that MT is upper triangular with diagonal entries lambda 1 through lambda n. Okay. Now, since MT is upper triangular, the previous result tells us T of Vk is in the span of V1 through Vk. So, in particular, T of V1 is equal to, well, in this case, it'll be the matrix of T's 1/1 entry, V1, which is just lambda 1, V1. Hence, T minus lambda I of V1 is equal to the 0 vector. Okay. Since P of T, Q of T equals Q of T, P of T for any polynomials P and Q over the same field at least, we have the following. We have, I'll write it this way, T minus lambda, I forgot to write lambda 1, right there, lambda 1 I, all the way down through T minus lambda n I, V1 is the 0 vector. Oh, okay. So T minus lambda I V1 is the 0 vector. Hence, because polynomials of an operator commute, we can say that T minus lambda 1I, which zeroes out V1, take a bunch of other stuff, that's just another polynomial, switch this over there. Okay, then we get 0 out from this. Nice. Okay, so we want to show that this thing right here is the 0 or is the 0 operator. An easy way to do that is to show that it sends a basis to 0. We've just shown that it sends V1 to 0. Now let's show it sends V2. Now, observe that T of V2, well, this is MT. Now think about it real quick. 1, 2, V1 plus the matrix of T. Now just write it down, 2, 2, V2. We're just using the fact that T of Vk is in the span of V1 through Vk. So in this case, we're saying T of V2 is in the span of V1 and V2. But I know what this is, right? This tells me that T of V2 is equal to, well, here, let me write it down real quick. Some multiple of V1, MT 1, 2, V1, plus, what's the 2/2 entry? Lambda 2, that's on the diagonal, lambda 2, V2. So, T minus lambda 2 I of V2 is equal to MT 1, 2, V1, which is in the span of V1. Oh, okay. Hence, T minus lambda 1I sends T minus lambda 2I V2 to 0. Oh, and using the fact that PT QT equals QT PT, again, we have that T minus lambda 1I all the way down through T minus lambda Ni V2 is equal to 0. Oh, okay. Repeat this process to show. Now, we're just going to keep going. Kind of the exact same thing. Exact same trick. We'll just write it out and just show that t minus lambda 1 I all the way down through t minus lambda n I vk is equal to 0 for k between 1 and n. Okay, nice. Here's how we do it. We're going to keep showing these pieces right here. We'll just add more and more terms. So it'll be t minus lambda 1i, t minus lambda 2i, t minus lambda 3i, v3 is 0. Then we keep going down to 4 with v4 equals 0, and so on, all the way up to n. It's the exact same procedure every time. Okay. This tells us that t minus lambda 1i all the way through t minus lambda ni, that big product, is 0, since it is 0 on a basis of v. Huh. Nice. That's what we wanted to show. Very cool. So, if you take t to be an operator on a finite dimensional vector space, if it has an upper triangular matrix, then t minus the diagonal entries times I, that big product, is equal to the 0 operator. Whoa, very cool. In the second part of this section, that's what we'll do next time, we're going to use this observation here that tells us that this polynomial, z minus lambda 1 all the way down through z minus lambda n, this guy here is a polynomial multiple of the minimal polynomial of t. In fact, if you look at it closely, it's monic, isn't it? It's a monic polynomial. Maybe it even is the minimal polynomial of t. We'll find out. We'll see what goes on. So, we'll find out more next time. Have a great day.